Hi, this is part one of a two-part video on machine-generated text detection. Part one is about DetectGPT, kind of a paper walkthrough of this paper, and part two will be about how we added on to this work and explored multiple methods available for this and performed red teaming attacks on them to see how they hold up against real-world scenarios. So DetectGPT is a zero-shot technique, which means that it does not need any labeled examples. It does not need like a large data set to tell it what it needs to classify against. All right, so the motivation behind choosing this was kind of how accessible and how crazy it is that LLMs are getting better each day, and right, so the increasing availability and usage of LLMs, and how there's the concern of misinformation, the concern of integrity of information available, and concerns over plagiarism in creative content and any other content, academic content as well. Navigating the ethical and legal challenges that comes with how accessible these solutions are to almost everyone, and how efficient current methods are in detecting machine-generated text without having to train an extensive model on like a large data set. And the availability of such a large data set is a concern in itself. And so a zero-shot technique seemed like a good option for this. This paper was actually published June of 2023, and then they added onto it with like an updated version called Fast DetectGPT, and this kind of opened it up to other zero-shot techniques such as Detect LLM, DNA GPT, and a few more. And we kind of I'll kind of talk about it in my second video, because we kind of explored all of these methods, examined them, studied how they performed in a real-world scenario, and tried to perform some red teaming attacks on them. So that will be in part two. So the problem description is that we are trying to detect whether a particular passage was generated by a particular LLMP. To be noted is that DetectGPT uses this description where it can only score, it can only optimally score against the exact LLM that was used to generate the text itself, which is kind of a limitation right now, but I'll get to that. So yeah, we detect whether the passage was generated by the particular LLM. We need the LLM's log probability function to kind of score the passage and other samples against, to be able to detect whether the sample itself was generated by this LLM. All right. The hypothesis behind this method, this approach for DetectGPT, is that the minor rewrites or like small perturbations of this model generated text is almost always going to have a lower log probability under the model. So this is the log probability curve for different samples, and so the samples in the middle are the fake and real samples, and then we generate a few more samples by applying perturbations on them using a smaller LLM like a T5, and we produce like minor rewrites, minor word switches, like just change the model, change the text a bit, and then we again estimate the log probability against the model and kind of plot it, and we see that almost always in the machine generated sample it is going to be lower, because this stems from the fact that an LLM would almost always choose the most optimal sequence of words when it generates any text, and any other perturbation is going to have a lower log probability with that model, right? So this is the idea behind DetectGPT's formulation, and we can see how if it was a human generated text, well, it's not going to be the most optimal sequence always, and we're going to have some perturbations that are going to be better, some perturbations that are going to be worse according to the LLM, and as the number of perturbations samples that we take increases, this is gonna average out to being close to what the human said. And so that's where I'll get to that. So we kind of determine the we kind of determine the difference between these two log probabilities, and we call that the discrepancy gap, and use that to kind of as a discriminant as to whether it was human generated or machine generated. All right, so the LLM's probability function is the function which estimates the likelihood of a sequence of words occurring in a given language according to the LLM, and zero shot, so it does not require any fine tuning, and the performance measurement ARC was used for this. And we do not need the model parameters or the architecture, but we do need the ability to kind of use the model and score it against these different samples. All right, so this is the discrepancy gap that I was talking about. We have the log probability of the original sample here, and we kind of perform an expectation that is almost like an average on all the log probabilities of the perturbed samples, and the difference between them is going to be called the discrepancy gap. And yeah, for a human generated sample, the expectation of the perturbed sample is going to be close to the human generated sample, so it's going to be close to 0, the discrepancy gap. And since this is always going to be higher for a machine generated text in comparison to these, this is almost always assured to be positive or much larger. So, and that's what we see as well. So tested on GPT-2 XL, we can see how the testing on multiple samples, multiple passages, we see how this discrepancy gap is much higher for the model generated text, and much lower and closer to 0 for human generated text. And this is kind of the main idea where DetectGPT uses to determine whether it was human or model generated. Excuse me. All right, so the methodology is kind of what we talked about so far. We get the probability on the initial sample. We use T5 or any other small LLM to kind of generate some perturbations on this. We pass all of these samples and get their scores as well, compute the log probabilities, compute the discrepancy gap, compare with the threshold, and there we go. All right. So they use kind of multiple data sets. So they use like to cover a variety of everyday domains and the use cases for LLMs. So they use news articles from the XM dataset to represent fake news detection, Wikipedia paragraphs to represent from the Squad dataset to represent academic essays that are machine written sometimes, and prompted stories from Reddit writing prompts to detect machine generated creative submissions. So yeah, they use 6 datasets, I believe, and tested on all of these. For each experiment, they generated the text by prompting with the first 30 tokens of the real text, and used AUROC as the performance metric. And all experiments have an equal number of positive and negative examples. All right. So these are some of the results that they obtained. We can see how DetectGPT consistently performs better than other zero-shot techniques, such as using just the log probability, rank, log rank, or entropy across different LLMs. So these are some open source LLMs that they tested against, and across multiple datasets as well. So this is the XM dataset, which was the news dataset, the Squad dataset, which was the Wikipedia paragraphs and writing prompts, Reddit writing prompts. All right, and consistently DetectGPT seems to perform well. And this graph shows us how the detection performance varies as the fraction of the paragraph written increases, that is rewritten. So the more we perturb the sample, the less likely it is going to look like a machine generated text. So detection performance decreases, which makes sense. And this is how it compares on the different datasets. So they saw how DetectGPT performs consistently well across even like different domains. So this was a PubMed QA dataset where, so in the initial XSUM and WMT, these two methods slightly better than DetectGPT, but they did not do well in a different domain. So DetectGPT is able to work across domains. It is not specific to any one domain, and maintain a decent performance. So we still have 96% and 83% in this case. So I believe this is the English dataset and this is the German dataset as well. So yeah, cross-domain performance was observed in DetectGPT. All right, and so yeah, we saw how we need to score the samples based on the base model that is used to generate the sample itself. But they also saw how it compares when we use a different scoring model, which is, of course, it is optimally, the detection is optimal only when we use the same model to score as the model that is used to generate. But yeah, this is that, and then this is how the detection performance varied with the length of the passage, and this shows us how it varies with the size of the perturbation model and with the number of perturbations as well. So as the number of perturbed samples increases, the more likely that the human generated text is going to the expectation of the log probability of the perturbations on the human generated text is going to be close to zero, close to the human generated text itself. So yeah, as the number of perturbed samples increase, it's going to take us more compute, but of course it's going to provide us a more accurate discrepancy gap, right, due to the random nature of it. And yeah, and to conclude, it kind of opened it up to other zero-shot techniques, as I said before, and explores the discriminative nature of the log probability function. So it is kind of an implicit watermark of LLMs, in the sense that the fact that LLMs are always going to be trying to generate like an optimal sequence of words to provide like a good proper sequence of words, it kind of implicitly watermarks itself, its outputs, as being machine generated, and kind of an implicit watermarking that lies within it, which could be exploited. And the assumption of being able to use the LLM's log probability function is a limitation, and the quality of perturbations is also another limitation. All right, because the quality of perturbations is a limitation because it could not represent real scenarios. It could make the text no longer maintain context or the same quality as the initial sample, which is kind of what we explored in part 2. I'll talk a bit more about that in part 2. So yeah, the potential future works is better perturbation functions, which give a more real world scenario kind of perturbation, where people are going to get some stuff of an LLM and try to modify that. So try to be more representative of a real world scenario instead of just randomly replacing some words. And knowledge about the LLM could be incorporated to improve detection. Use an ensemble model for scoring. Determine the relation between prompt and detection. Explore the use of watermarking in generator models in other domains, such as image generation and audio generation and all that. So yeah, all right. We kind of wrapped up this presentation. So this was actually part of my presentation for CSAI 544, Applied Natural Language Processing. So we kind of ended the presentation with this question, where we ask, as the models continue to improve in capability, will it be possible to even maintain the ability to distinguish between what's machine generated and what's human generated? And I will end this with that as well, and I will talk more about what we worked on in part 2. All right, thank you.